All right, so we are talking vectors. This is chapter 12, section 6, vectors. Our learning objective is to use basic vector operations and the dot product. A vector is a mathematical object that has both a magnitude, which is a size, I like to think of it as a length, and direction. We've already written that here. You often use an arrow to represent a vector. The magnitude of a vector is the length of the arrow. So you can, so it looks like this, denote it as, it looks almost like an absolute value, and then a bold V in the middle. You show the direction of a vector by the initial point and the terminal point of the arrow. So if you want to find the magnitude of the vector, you take the A component of your terminal point and the B component of your terminal point and use the little Pythagorean theorem. Okay, so let's start doing stuff with this. All right, I have a vector here in problem number 1. He starts at 1, 2. And he goes from 1, 2 all the way to 8, 5. Now, the sad part is I really can't use this vector unless he is moved down. So I really need him to start out here. So I'm going to take this coordinate and go, I need to subtract 1 and 2 from each of my coordinates to get back to the origin. So 8 minus 1 is 7, and 5 minus 2 is 3. So I go over 7, up 3, which is right there. And in fact, my line, if I put it at the origin, is right there. So now I know if I am at the origin, my vector is 7, 3. And that is in component form. So component form means my starting point is at the origin and it ends wherever it ends. So what are the component forms of the two vectors shown here? So the first thing we're going to do is we're going to take this vector here and move him to the origin. So to do that, I have to add 1 and minus 4. So I'm going to add 1 and minus 4. When I do that, I get -1, -6. 1, 2, 3, 4, 5, 6. So really my new line is going to be right here at -1, 6. Boop, boop. So in component form, he gets to be -1, -6. All right, let's take our next item and do exactly the same thing. We are going to move him from, he starts here, so we're going to move his starting point. This is 2 minus 1. So in fact, the end point is going to be at 3, 4. So if he starts at the origin and he goes over 3, up 4, that line is out. Be right there. Let's take and narrow down that line. There we go. Go back to my baby line. So in fact, our other one is 3, 4. So really you want to just move it to the origin and see where it is based on origin. All right, so we can also write it in matrix form. See, now we're bringing it back to what we got going on. So we can write the vertex as, instead of A comma B, we can write it as AB. By writing in matrix form, you can use matrix transformation to transform a vector. So, like if we want to rotate the vector by 90 degrees, what is the component form of the resulting vector? So we write it, and we multiply it, and then we get the resulting vector. So let's do that for ours. Rotate the vector v by 270 degrees. What is the component form? So a 270 degree rotation is multiplying by the matrix 0, 1, and negative 1, 0. So we're going to multiply negative 3, 5 by that. And when we do that, we get 5, 3. What other matrix transformations can you apply to vectors in matrix form? Well, just so we can get done with our work today. So if we have 2 vectors, so here we go. We got operations with the vectors. What else are we going to do? So we have vector v, vector w. We're going to add them together. So adding 2 vectors, we add their first component and their second component. Awesome. To subtract them, we subtract their first components and second components. And when we want to multiply it by a scalar, we multiply each component by that scalar. So note that w plus v minus w is equal to v, and v minus w plus w is equal to v. All right, so let's see how this looks. So let u equal negative 2, 3, v equal 5, negative 2. What is the magnitude of u plus v, rounded to the nearest hundredth? So we have to first find u plus v. And there is tip-to-tail method that we can use. So the first thing we do is we draw u. And then at the tip of u, you draw 5, negative 2. So if you look at that, here is u. He goes negative 2, 3. And then at the tip of u, you draw 5, negative 2. Here's u, sorry. So you go to the right 5 and down 2. 1, 2, 3, 4, 5, down 2. And then the 2 together is this dashed vector right there. So draw u plus v to have the initial point of u and the terminal point of v. Express u plus v in component form. So if you look, start back at the origin and end where v ended up, and you have 3, 1. So now that we know it's 3, 1, we can use this little formula, 3 squared plus 1 squared square root, and you get 3.16. So we're going to check that work by actually adding these. What is negative 2 plus 5? It's 3. And 3 plus negative 2 is 1. Using the vectors given in problem 3, what is u minus v? And I think we can easily go negative 2, 3, minus 5, negative 2. So that is negative 7 and 5. So the magnitude of that is negative 7 squared plus 5 squared. Calculate that in the calculator and we can get a nice approximation. Negative 7 squared is 49 plus 5 squared is 25. You add those together, it's 74, and you take the square root and get approximately 8.6. All right, scalar multiplication. We are going to multiply our guys by what it tells us and then graph them. So let me get just a simple graph going. All right. So in problem A, we are going to take our u and we're going to multiply it by negative 1. So to draw this vector, we're going to go start at the origin and go over 2, down 4. Yay! Okay, so now we're going to take our vector u and we're going to multiply it by 1/2. And when we do, we get negative 1, 2. So now go negative 1, 2. And that is that one. Easy peasy, basic. All right, so let's get to our second part of the learning objective. If vector v1 and v2 and w1, w2, the dot product, which is kind of like vector multiplication, but a little bit different. The dot product is v1 times v2 plus, v1 times w1 plus v2 times w2. If when you do that, you get 0, the two vectors are normal or perpendicular to each other. So now we're throwing the word normal in, and it actually means perpendicular. So let's see. Are the following vectors normal? So are they perpendicular to each other? So you go find the dot product. So 2 times 7 plus negative 5 times 3. So that's 14 plus negative 15 is negative 1. They are not normal because it does not equal 0. So you can check that by finding the slope between the 2 points. Finding they are not perpendicular. All right, so let's try that on our own vectors. Let's go. We'll call this u and v. So u dot v is equal to negative 2 times negative 9 plus 6 times negative 18. Negative 2 times negative 9 is 18, and 16 plus negative 18 is 108. Well, we know this definitely does not equal 0. And it's negative 90. I got it. So these are not normal. And that's all you got to do.